smoke is getting less and less every day. So today we're going to take really a little step further in the theory, okay? We're going to a class of systems that really are significantly more general than the piecewise affine maps that we've been studying. So if you remember, our first model example will be the Gauss map. F of x equals 1 over x, 1 over x mod 1. And this is full branch in the sense that it has a partition. In this case, it's an infinite partition. Like this. Okay. But it's not piecewise affine, okay? And we showed, I left as an exercise to show that it has an invariant measure. So, where's our measure? So the measure mu, and mu of a is equal to 1 over log 2 integral of 1 over 1 plus x. The x is invariant. And what we're going to prove today is that it's ergodic. But actually we're going to prove something a little bit stronger. Is that, so we're going to prove a theorem that says that mu is invariant and ergodic. And if you remember, one of the key points of the ergodicity proof. So let me introduce, at some point in the ergodicity proof I emphasized that there was one step that used the fact that the derivative is constant, okay? So the problem here is that the derivative is not constant, and I want to introduce an important fundamental concept, which is that of distortion. So definition for any subinterval j 0, 1 and any n greater than or equal to 1 such that fn from j to fn of j is a diffeomorphism. We define the distortion dfn of j is equal to supremo for all x, y, and j of the log of the derivative of fn in x over the derivative of fn in y. So this we need a little bit of time to get familiar with, but let's look for the moment just at n equals 1. Okay, e.g. n equals 1. Then we have that the distortion of f on some interval j is equal to the supremo over x, y, and j of the log of just the derivative. The derivative in x over the derivative in y. So suppose the map is piecewise affine, right? Like the examples we gave it. Suppose J is one of the intervals of the partition. Then what is the distortion of F on each interval of the partition? Sorry? Is 0, right? Because the piecewise affine means exactly that on each interval of perturbation the derivative is constant. Okay? So dfx equals dfy, so this is 1, log of 1 is 0, so the distortion is constant. Yeah? The distortion is 0. There's no distortion. So what about here? Here you have some distortion because you have the derivative is different at different points. Right? So here you have, at some point, you have a certain value of the derivative, at another point you have a different value of the derivative. What's going to be, at which 2 points is this supremum going to be achieved? You're looking at the ratio between the derivative at different points. So we only really look at inside each element of the partition one by one, right? Because we assume that the map F is that the derivative is defined at all the points. So we don't look at the whole interval because there's some discontinuity points here. So we just look at one of these. So where is that supremum? Which 2 points is going to maximize that? The extreme points, right? Because that's where the derivative changes most, right? The ratio between the derivative at this point and at this point is going to give you the supremum there. Okay? So in some sense, this distortion tells you how the derivative, how much the derivative is changing. Okay? So the derivative in some cases can be also infinite. So for example, if we take the quadratic map like this, remember we looked at this quadratic map here. This is also full branch. For this derivative, it doesn't need full branch, but we take one of these elements here. Suppose J is this, or either the whole interval or even just half the interval. What's the distortion on J? The distortion of the map on J. It's infinite. Why?
Because I will look at the extremes.
Yeah.
So in one extreme the derivative is 0.
Exactly. That's all you need, in fact. If there's one point where the derivative is 0, then it means you can put a 0 on the bottom, so you get an infinite distortion.
Yeah, a lot of 0 or something.
Yeah? So if there's an infinite derivative, if there's any point where the derivative is infinite, or any point where the derivative is 0, then the distortion of that interval is infinite. Okay? And now we will give, let me immediately give a lemma which gives a more geometric intuition for the meaning of this distortion. And then we will see how we use this to prove how this plays a crucial role in the ergodicity, because it's a kind of generalization of the piecewise affine. If the distortion is controlled, then it's good enough to get what we want. So this is most useful to really get a feeling for why we introduce this concept of distortion, is that let D equals D of F and J. Okay, so let's suppose we have a situation like this where we calculate the distortion. Then for all subintervals J in J, J prime in J, we have the following, that we compare the image of J prime over the image of J. So we're going to look at the following pictures. So we have an interval J. It maps by Fn to Fn of J. Okay, and then inside here we have an interval J prime that maps to the image. This is Fn of J prime. Okay, and if you remember, what is the key point where we use the affine property of the map in the proof of ergodicity was that these proportions stay the same, right? So that if the map is affine, then the proportion between J prime and J is preserved when you map everything by f of n, and so the proportion between f and J of prime is equal, the proportion between f and J of prime and fn of J is equal to the proportion between J prime and J, okay? And here what we get is a bound, so we look at the proportion between the images, and we get that this is less than or equal e to the d times J prime over J, and less than or equal to e to the minus d, also J prime over J.
When f is affine.
Sorry?
When f is affine.
No, when f is affine, then you get the distortion is 0, right? And when f is affine, the distortion is 0. So this is just 1, this is just 1. So you get squeezed on both sides by, you just get equality. You get f and J of prime. You get this ratio is equal to this ratio when it's affine. Okay? So what we're saying is that the distortion gives you some bounds where it's not, this ratio is not equal, but it tells you that there's a bound, right? So if you look, if you know what this ratio is, and you look at the images, and you want to know what this ratio is here, then there's a bound as to what can happen here.
So why do we look at log, the supremum of the log, not the...
In many calculations where we use the distortion, it's natural to have the log there. Okay, but of course, if you wanted to, you could define it without the log. It's also natural because it gives 0. Distortion 0. You know, when you think about distortion intuitively, in the affine case, here you get distortion equal to 0. But of course, you could just define it differently way and then not take the exponential here and take the log where you need to take the log. It doesn't matter. But it just turns out to be more useful to define it like this. Also because by the chain rule, we will get some kind of sum of the distortion. The distortion of the iterate is kind of the sum of the distortion in some sense, as we shall see. Why does this, how does this apply here? Can you see why when you have, here you have infinite distortion, right? So this suggests, although this is not what the lemma says, right? The lemma says that this is a bound, but of course in principle it might be much better bound. But in principle, why is this lemma false in this case where we have infinite distortion? Why is it that if you take J and then you take f of J is this whole thing, right? And then you take a subinterval, J prime here, right? And then you take the image, so this is, the whole thing is f of J, and then you take f of J prime, right? And we're comparing, remember, so what we're doing is we're comparing the ratio between this interval here and the whole thing, and we're comparing the ratio between J prime and J, right? So can you see why in this case this can blow up, the difference between these two ratios? What happens as you get very close to 0 here, or to this critical point here? If this is a quadratic map, so this in fact is the map f of x equals x squared equals 2 minus x squared. So this is a quadratic critical point here. So if you take a small interval that is very close to C, then what's the size of the image of that interval? How much smaller? If we take an interval of size epsilon here, it's square of epsilon. Is the square of epsilon. If you take the distance, if you take an interval that contains the point C, actually that's the easiest. If you take an interval that contains the point C, this is size epsilon, and its image is the size epsilon squared. Okay? So here you can see that you have intervals that are very small. So this is of the order 1/2 or order of 1 roughly. You take an interval of size epsilon and its image is of size epsilon squared. So it does not have a uniform bound, right? You look at the ratio between this and the image will be of the order epsilon squared, whereas this will be of the order epsilon, and you cannot get uniform bounds like this in that case. Okay, let me leave this as an exercise. Consider, this is an important exercise to really get a feeling. Let fx equals, let me write that particular map, although any map with a quadratic critical point will do, and show that the conclusions of the lemma show that well, in this case, the distortion is infinite, so in some sense this still holds in some sense when you have this infinite, but show that there does not exist, that there cannot exist any constant k greater than 0 such that fj prime over fj less than equal to k j prime over j 1 over k j prime over j for all subintervals j prime and j. Okay? In other words, the conclusion of this lemma with uniform bounds, so the key point here is in some sense that there exists uniform bounds here for any subintervals. Right? The fact that this uniform bound is given exactly by this formula for the distortion is something that is useful because it allows us to control the uniform bound and to know exactly what it is. But in some sense, the key point is just that you have uniform lower bounds. So it doesn't matter where you take the interval, okay, then you know automatically that the ratio between the size of these will be essentially preserved up to some multiplicative constant. And in fact, moreover, we know exactly what this multiplicative constant is. Whereas in this case, what I want you to show to get a feeling for this is to do an exercise to show that independently of the definition of distortion, you cannot get a uniform bound for this ratio that does not depend on j prime. Right? Of course, for each j prime you can get some, but if you fix a constant and you take j prime very, very close to the critical point here, then the ratio between these two will be much, much smaller than the ratio, and so it will not be bounded below by 1 over k. Okay? So the intuition between distortion, the intuition behind distortion is simply that it's measuring how mass is distorted. Remember, we're talking about measures. In the end, what we're interested is in how measures. We're looking for invariant measure and ergodicity. One of the things we use in the proof of ergodicity is the fact that invariant measure, the piecewise affine maps preserve the ratios between measures of sets, and this is saying that if you have a bound on the distortion, then it almost preserves the measure of set. Okay? Now this is for one particular iterate, right? Now what happens, now let's look at the, shall we prove this lemma or not? I think I will leave it as an exercise. It's really 2 lines using the mean value theorem, and it's in the notes. So why don't you, and it also is useful to go through it just to, okay, it's just an application of the mean value theorem and you get it. Okay, it's very simple proof. So what do we want to do with this? So first of all, let me say what is the problem with iterating. So Let's look at the Gauss map, but any map will be, or let's look at a more generic map. So let F01, 01 be a full branch C1 map. Okay, that means that each branch is a C1 diffeomorphism. So we have, let me just draw a finite number of branch for the moment, just to for example, something like this. Okay, and let's suppose that the derivative is bounded away from 0 to infinity everywhere. Okay, so suppose that df of x is greater than equals some delta less than equal to 1 over delta. Okay, greater than 0. The absolute value for all x. Okay, so what does that mean? That means that for each on each j, the distortion is bounded away from 0 and infinity. Okay, the distortion is bounded. Okay, so distortion of f and j is bounded less than infinity for each j in the partition. Say we have some partition P0. Okay, full branch C1 map with partition P0. Okay. So, what are the natural domains for the partition for the distortion of the second iterate? Let me actually maybe call this partition P1 because it's more natural in this case. Yeah. Okay, so P1 is this partition that we start with. Okay. Now remember we looked at full branch maps. What is the structure? What does the second iterate of this map look like? Do you remember? Will it be still a full branch map?
We have again same partitions in each G.
Exactly.
Same and
Yes, so each one, when you look here, we define the same elements of the partition, and then you see that each partition element is divided into, if there's 4 elements, then each one here will be divided into 4 subintervals. Each one maps to one of these after one iterate, and then maps to the whole thing after 2 iterates. Yes? So in the end, we will have a partition of, so P2, so here we have 4 elements. The cardinality of P1 is equal to 4, for example, in this case. And then we have a partition P2, which is 4 times 4, which is 4 squared, right? Which has 16 elements. And F2 is a full branch on this partition P2. Okay with that? Everything okay with that? Yes? So now, these are the natural domains on which we want to calculate the distortion of the second iterate. Right? So what will be the bound? Can we bound the distortion of the second iterate in terms of, for example, is it the same as the distortion of the first iterate? So here we have that we can define the distortion on each of these 4 elements. For all j in P1, it's finite. So the maximum of all these 4 is just some finite number. And what about this? Can it get worse?
I think the worst it could get is twice as much.
It can get worse, though. You think we can control it?
Yes.
Yes. How can it get worse, first of all? Why can it get worse?
Because the map gets for the slope increases.
Yes, and so?
And so we have more values for the numerator to grow.
Yes, but why does that show that it can get worse?
Is the same delta square delta minus 2.
Yeah, so the way I can see it, I think there's probably several ways to see it. I see it like this, as what we said before, right? So if you look at the distortion of this interval, then the worst, you look at the smallest point, the derivative where the derivative is smallest, you look at the derivative at the point where the derivative is largest, and you take the ratio, and that's what gives you the distortion at that point, right? The worst case between x and y, okay? Now, when you iterate twice, what are you doing? You're taking 2 points from here, and then so you take 2 points from here, say, and then you look at the ratio, the log of the ratio between the derivatives there, and maybe you're unlucky and you got exactly those 2 points that give you the worst distortion, right? And then you map them, and now they belong to some other iterate. So for example, you map them and they belong to here, and then you look at the derivatives here and you compose the derivatives, right? So this derivative here, so maybe I should write, so the derivative of f2 of j is supremum over xy in j of df2x over a log of df2x over df2y. But what is the derivative? Remember that df2x is equal to dfx times the derivative in f of x by the chain rule, right? Is the product of the two. And then you have df2y is equal to the derivative between the f and the f of y. Okay? So you're right, it can get worse, because it could be that now if you're unlucky, then this df of x is the place where the derivative is worse, okay, amongst all the xy where you begin with, and then when you take df of x, this is also less than df of f of y, and so you are kind of getting the worst in both cases, right? So it is getting worse. So as you take the distortion of larger and larger iterates, you might be getting worse all the time. So it could be that it's difficult to control, right? So if you take n very large, then you take very small intervals, and what you're taking is you're taking 2 points in these very small intervals, and you're iterating them many times, right? So you're iterating them in the interval in which they begin with, and then they're moving to another interval, and you're iterating them there, and then you're iterating them there, and you're consecutively looking at the product of all the derivatives and the product of all the derivatives here, and it can be that this is just getting less and less and less and less, and this is getting bigger and bigger and bigger and bigger, and they're diverging, and the ratio between them is just getting worse and worse and worse. Right?
Can it stay the same?
It can also. So this is what we're going to define. So a very fundamental property. Yeah?
Okay, but it cannot get better. Or can it get better?
No, it cannot get better.
Because we sum log.
Yes. Yes. I mean, I don't know if that's a form of theorem that it can get better, but probably you can see that it cannot actually get better. I'm not sure if there's a strict inequality that says it always has to be worse. But certainly, in general, it'll get worse. Right? And now we have this definition that a full branch C1 map has what we call bounded distortion if you take the supremum over all n greater than or equal to 1, and then for each n you take the supremum over all the intervals of the partition omega n in Pn. So you look at the refined partition, right, which is the one on which Fn is defined, and then we take the distortion of Fn on omega n. And this should be finite. So what this is saying is that it can get worse, but it cannot just keep getting worse. Now this seems like a very ambitious aim. Okay. In the case, so this, if we write this, sometimes it's useful to write this actually as with the full. So this is really supremum n greater than equal to 1, supremum of omega n in Pn of the supremum over all x and y in omega n of the log of dfn of x over dfn of y. Right? This is what that distortion is. So if the map is piecewise affine full branch, then it's okay. Right? Because if it's piecewise affine, this is always 0. So this is 0. Okay? Intuitively, if it's not piecewise affine, we can see how this might just go to infinity. So when you take especially this supremum, in general here you will always have some finite terms. When you take 2 in one of these partition elements, and even when you take the supremum over all partition elements, you may expect this to be finite, but you're taking the supremum over all n, so you're taking higher and higher iterates, and every time you take a higher iterate, in principle, this can blow up. Okay? But it seems we will see that there is this intermediate case. The piecewise affine is always 0. In general, this may blow up, but there are some cases which have bounded distortion. Okay? So what we're going to do now is 2 steps. First, we're going to show that bounded distortion implies ergodicity. And then we're going to give some criteria to check bounded distortion, because bounded distortion is not an easily checkable condition, right? In fact, maybe I will do that first, actually. Maybe we will first check that the Gauss map satisfies. We'll first give, let me first give the ergodicity proof for this. So the theorem, yes?
Here in this, the 2 derivatives that he wrote down,
Yes.
these 2, if we look at their ratio and consider the log,
Yes.
then it would be the sum of
The sum of the logs.
the sum of the logs, and one of them would be the original
Yes.
thing.
So it's always getting worse, yes.
So it's always
Yes, you're right. It's always getting worse, yes. The question is whether it keeps getting worse and worse and worse and worse, or whether it gets worse but a little bit less worse each time. Okay, so let me write the theorem.
But for the map we're working on, the derivative is always bigger than 1, right?
So this is going to be one of the features that will allow us to prove bounded distortion, yes. That is going to be one of the key characteristics, one of the key properties to be able to show that specific maps have bounded distortion. Because as you look at it like this, it's not a very checkable condition, because this you need to iterate all the map infinitely many times. You cannot just check it by looking at the map. Okay, so I will give in a second a proposition that tells you that if a map satisfies some condition, then it has bounded distortion. Okay, but first I want to motivate the bounded distortion by the following theorem. If f I is a full branch C1 with bounded distortion, then Lebesgue measure is ergodic. Even if it is not invariant. Right? Remember that the definition of ergodicity does not depend on invariance, right? It's just definition of ergodicity. Now, why do we care if Lebesgue measure is not ergodic? Why do we care? It is not invariant. Why do we care if it's ergodic? So we have the simple lemma that says that if mu1, if just completely general, fi to I is a measurable map, and mu1 and mu2 are probability measures, with mu1 absolutely continuous with respect to mu2. Okay. Then, if mu2 is ergodic, it implies mu1 is ergodic. So the proof is very simple. I will give it in a second. But how does this? Why is this relevant to our situation?
Maybe we can make mu1 invariant.
Yes, like in the Gauss map. Right? In the Gauss map, we found already the invariant measure, and the invariant measure is absolutely continuous with respect to Lebesgue. Remember, we have the formula for the invariant measure with integral.
Yes.
Right? So what does that mean? That putting these two together, we get that this theorem tells us that Lebesgue measure is ergodic, okay? But we just showed that the Gauss measure, the Gauss map has a Gauss measure which is invariant, which it does not matter if it's invariant, which is absolutely continuous, okay? And therefore this lemma implies that the Gauss measure is also ergodic. Okay? So these two, so theorem, I didn't have numbers, but these two theorems together, these two lemmas together, imply that the Gauss measure is invariant and ergodic.
But we need to prove bounded distortion.
Sorry?
First, I think we need to prove bounded.
Ah, yes, sorry, we will show that. Yes, so we need to show, yes, so, yes, thank you. Once we show that the Gauss measure has bounded distortion, then this will imply that. Okay, so we will do that later, so you're right, let's just leave it for the moment. So these are the steps, in fact, so we will, so, and then after, okay, so let me state that let me write this as a proposition maybe. Proposition, which we will prove also, is that the Gauss map has bounded distortion. Okay, and these three together imply that the Gauss measure So maybe why don't we have just a little break, 2-3 minute break, and then we will start the proof of this. So first of all, let's prove the lemma. It's very simple. So proof of lemma. So we need to prove that mu1 is ergodic. How do you prove that something is ergodic? In general, in an abstract setting, the basic principle is you assume that mu1 of A is positive, you have some positive, and you show that it has full measures. Okay, because that's what the definition of ergodicity says. Okay, so very simple chain of implications. If mu1 of A is positive, then what does that say about mu2 of A? Then it must be also positive, right, by absolute continuity. Because absolute continuity says that if it's 0, then this is 0. Okay? So this is positive. This is by absolute continuity. Mu1 absolutely continuous. Mu2 implies this. Okay? But mu2 is ergodic. Okay? So this implies that mu2 of A is equal to 1. This is by ergodicity of mu2. Okay? And this implies that mu2 of A complement is equal to 0. And what does that imply about mu1 of A complement? Is also equal to 0 by absolute continuity. Right? Equal to 0. And what does that imply about mu1 of A? Equal to 1. Looks like magic, huh? We're cheating. But it's just, actually, that's why it's a very simple. Somehow the ergodicity, because of the way definition, because of the way ergodicity works, every map that's absolutely continuous with respect to an ergodic measure is also ergodic. Okay, so that is why proving that Lebesgue measure is ergodic, in particular for the Gauss map, so combining these two will show that the Lebesgue measure is ergodic for the Gauss map, which is a stronger statement, slightly stronger, but a bit stronger, than saying that the Gauss measure is ergodic. Okay, it just means that every absolutely continuous measure is ergodic. Of course, we're particularly interested in the Gauss measure because it's also invariant. Okay, so we obtain that the Gauss measure is invariant and ergodic. Okay, so what about the proof of the theorem? So proof of the theorem, I'm going to cheat a little bit because I'm going to ask you to remember the proof for the piecewise affine case. So do you remember how we did for the piecewise affine case? So proof of this theorem, right? So here we're replacing, if you look at the statement, we're replacing affine with bounded distortion. Okay? Our conclusion is the same. Lebesgue measure is ergodic in the piecewise affine case. And now we're saying that bounded distortion is sufficient for us to get ergodicity of Lebesgue measure. If you look at the proof of ergodicity of Lebesgue measure in the affine case, we did not use the fact that Lebesgue measure is also invariant.
Yeah, we use the Lebesgue density theorem.
We use the Lebesgue density theorem, exactly. We do not use the invariance of Lebesgue measure. Okay? So the proof is almost exactly the same. So let me just review the key points, but so what did we do? First of all, we said let A, let A in 0, 1, in I, well in the interval I, which is forward and backward, which is backward invariant, right? And mu, and here we want to Lebesgue measure, so I'll use this notation here for Lebesgue measure, is positive. Okay, maybe last time I actually used Lebesgue. Okay, and we want to show that it has full measure. Okay, remember that? So what we did is we had, sorry, we need one lemma. We need one lemma. Sorry. Yes.
It happens, so we have some interval in A, which is this has a interval A more than this in this interval.
Exactly. So, okay, so before I state the lemma, let's get to the point where we need the lemma. Okay, so and then we'll see if you can, there's a lemma that we need to do as an exercise to actually prove this. Let's just remind of the argument. So we said that we had, by Lebesgue density theorem, there exists some n bigger than 1, remember, and there exists some omega n in Pn, where these are all the refinements, dynamically defined refinements of the partition, right, such that omega n intersection A over the size of omega n is greater than or equal to 1 minus epsilon. For all epsilon greater than 0, there exists this. Remember? We did that, yes? So we have our interval 0, 1 here. We have our set A here, of which we have know nothing about the structure, just that it has positive measure. And Lebesgue density theorem says that almost every point of A is a Lebesgue density point. If you take a sufficiently small neighborhood of that point, then most of the measure belongs to A. And then we want to find around this Lebesgue density points an element of the partition. Do you remember there was one lemma that we needed, or an observation we needed to make to get this statement here? Because we needed the omega n's to become sufficiently small. I don't know if you remember. In the piecewise affine case, it's almost obvious, so maybe we did not emphasize that. But in the piecewise affine case, these are getting very small. So to be able to show this, you need to say that these are shrinking to 0, these omega n's. Do you remember that? And in the piecewise affine case, we use the fact that the map is expanding. Because it's piecewise affine, the derivative must be bigger than 1 everywhere. And then we did an estimate, remember, for the size of omega n's is less than e to the minus lambda n. We had some estimate for the size of each omega n's. Okay? But here we don't have that. Here we just have bounded distortion. We do not know if the derivative is bigger than 1. Everywhere. Okay? So I'm going to leave this as an exercise, which I think is very interesting. It's in the notes, actually. It's a lemma in the notes, so you can see, you can follow that if you have difficulty doing it for yourself. But I think it's very interesting that actually what you need is just bounded distortion that does not say anything about the derivatives. And if bounded distortion implies that these, so the way I write it here is it implies that that the maximum of the size of the Lebesgue measure of these intervals omega n, where omega n is in Pn, goes to 0 as n goes to infinity. Okay, so in fact, all these omega n's are necessarily shrinking to 0. For each n, you take the partition Pn, you take the biggest of these partition elements, and this bigger, so it means that all the partition elements in Pn are uniformly bounded by some sequence that is going to 0, as n goes to infinity. Okay, and you need this to get this, right? Because this tells you that you can find small and small intervals. Otherwise, it's not clear that when you do this iteration, necessarily these intervals of these partition elements are shrinking to 0. So the fact that they're shrinking to 0 allows you to say that they are arbitrarily small and allows you to find this. Okay, that's the first step. And then from this, where did we use the second place where we use the piecewise affine property? Okay, if you remember, once we had this, we rewrote it as, let's see if I can recover the argument. So this implies, for the complement, we can write it as omega n intersection the complement over omega n is less than equal to epsilon, right? Because 1 minus epsilon of the measure is taken up by A inside omega n, so the complement inside omega n will be less than epsilon, okay? And this is where now we used the fact that it's affine. So what we were comparing then is omega n intersection AC over omega n, and then we wanted to compare that with the image of this, Fn of omega n intersection AC over Fn of omega n. Do you remember? And we put an equal sign here. This is equal because of the affine, because it's affine. Okay? And then we made one last step, which says that this is, so this is equal to AC over I. This is equal to the measure of AC. Of a complement. And then we had that this was, okay, this is less than equal to epsilon. I should have done it the other way around. Less than equal to epsilon. Okay? In case you don't remember correctly, this was the argument. Okay? So we had that we are comparing this. So using the fact that AC, this uses the fact that AC is invariant. F minus 1 of AC is equal to AC. It just implies this, implies that this is actually AC. This is equal to the interval 0, 1. So this is just 1. Okay? So this is actually the measure of AC. And here, by this Lebesgue density theorem argument, we get that this is less than equal to epsilon, and so this implies that AC is less than equal to epsilon for arbitrary epsilon. This is how we did it in the piecewise affine case. Any questions? Okay. So now we don't have piecewise affine, but we have bounded distortion. So what does the bounded distortion tell us? Here, exactly, right? So the bounded distortion is comparing this, the ratio between these sets and the ratio between these sets. Here. Okay? And it's telling us that this is less than or equal to e to the minus e to the plus, or e to the distortion of Fn on omega n. I should have had a bit more space, so let me write it. Give myself a little bit more space here. And then you write it here. So this is epsilon greater than or equal to omega n intersection AC over omega n. okay, greater than or equal to, and here, so this is less than or equal to e to the bounded the distortion of Fn on omega n. Because that's what the distortion says, right? Here I've not used the fact that we have bounded distortion. This is just by the lemma, the first lemma that I wrote, right? That said that if this is the distortion and you compare the ratio between two sets and their images, then you get this bound here. Okay? This is just the definition of distortion. But the fact that we have bounded distortion means that this is uniformly bounded, right? So by the bounded distortion property, dFn on omega n is uniformly bounded for all n greater than or equal to 1 and for all omega n dPn. That's exactly what the bounded distortion property says. It says that if you look at this distortion here, the supremum over all n and over all omega n's is less than infinity, which means that there's a bound that bounds all of them. Okay? And that means that you can put a constant here that does not depend on n. Okay? And since you can put a constant here that does not depend on n, then we have exactly the same situation. So we have this for every n, and so for every epsilon, arbitrarily small, we can find an n that this will work with the same constant, which means that this is bounded below. So here we'll end up getting the same constant here, right? E to the dFn of omega n. Okay, but this now is a constant that does not depend on n. So as epsilon goes to 0, this also goes to 0. So I've just sketched it, but basically it's essentially everything we did in the proof. So as you see, the proof is actually very simple, just like it was for the ergodicity of Lebesgue in the piecewise affine case. We just substitute the piecewise affine, and I remarked at that point, remember that the equality was not really necessary. All we need is an equality with some constant here, and this is exactly the constant, and the bounded distortion says that this constant is independent of n. This is the key point. If this constant depended on n, then we could say nothing, right? Because when you take epsilon very small, you take n very large, and then you might have another constant, and you cannot conclude that that goes to 0. So the key thing is that the constant does not depend on n, and that's what the bounded distortion property gives. Okay? So this proves the Lebesgue measure is ergodic if you have bounded distortion. Okay? So bounded distortion is a kind of relaxation of the affine property. Okay, good. So what's left is to verify bounded distortion. It's a non-trivial property. It's a very non-trivial property in general for dynamical systems. And we will now give some conditions which imply bounded distortion. So, as I said, what we would like to show is that the Gauss map satisfies bounded distortion, but we're going to prove a more general result. Okay, so let's first of all give a definition. So F I full branch is uniformly expanding if there exists constant c and lambda greater than 0, such that for all x in I, such that x, f of x, fn minus 1 of x is not in the boundary of the partition, right? So in other words, for all x for which this orbit kind of is differentiable, then we have that df n of x is greater than or equal to c e lambda n. Okay, this is just, don't worry about this so much. This is just saying when you have a full branch expanding map, you have these boundary points which always be problematic. We don't really need to care about them. Okay, for every n, for all x, and for all n greater than or equal to 1, such that you can talk about the derivative of fn in x, then this is uniformly expanding. So what is the difference? So notice if the derivative is everywhere bigger than 1, is this true? What is the meaning of this uniformly expanding condition here?
But isn't this bound like too big?
Too big.
Yes.
So let's say as an example is the case in which df of x is bigger than equal e to the lambda, which is greater than 1 for all x. So suppose the derivative is bigger than 1. Okay? So the derivative everywhere is bigger than 1, so we can write the bound as the form e to the lambda, because for some lambda bigger than 0, right? This is bigger than 1. Okay? And then what will we get for df n of x is equal by the chain rule to just the product of the derivatives along the orbits, right? So this will just be greater than or equal e to the lambda. Right? The derivative of df n of x is equal to the derivative df in x times the derivative df in f of x, okay, times the derivative in fn minus 1 of x, okay, and in each one this is greater than e to the lambda, so this is greater than e to the lambda. This is really the picture that you were mentioning earlier about saying that when you take iterates of the full branch, they get steeper and steeper. It's true. They must get steeper and steeper, right? You can see it either geometrically because you're taking smaller and smaller intervals which are always mapping full branch to the whole thing, so it needs to get steeper. And also because if the map is expanding, then the derivative is growing exponentially fast. So you have intervals that are shrinking exponentially and the derivative is growing exponentially. That gives you a more quantitative description of the fact that these graphs are getting steeper and steeper. Yeah, this is just what's happening. As you iterate, you get steeper and steeper, and the derivative is getting bigger and bigger. Okay. The reason for this C is just a little technical kind of, but fairly important subtlety, is that there may be some point, as we shall see, for example, the Gauss map. The Gauss map, we're going to check, in a second I'm going to leave you as an exercise to check that the Gauss map is uniformly expanding, and the Gauss map does not satisfy this, because the Gauss map, the derivative at 1 is equal to 1. Okay? So in the Gauss map, the map is equal to 1, so you do not have this property here. Okay? But you still have the second iterate of the Gauss map is uniformly expanding. Okay? And that means that you may have some maps that are not uniformly expanding. You may have some points where the derivative is equal to 1, or you may even have some points where the derivative is strictly less than 1. Okay? But because of the geometry of the map, you might have a situation where these points, after one iterate, they map to points where the derivative is large, and so it compensates the fact that they have small derivative, and so some iterate of the map has derivative bigger than 1 everywhere. Okay? And this C takes into account this C may be small. In general, this C may be, for example, 1/10, 1/1000, 1/1,000,000, and it tells you that if you take n small, this might be small. So you might have a point where when you take n equals 1, the derivative is very small. So if you don't have the C, this would be false. It would not be true. Okay? So you put a small c here to take into account those initial iterates, but you see the c becomes negligible when n becomes large, right? Because as n becomes large, this is going exponentially fast, so the c does not really matter. So the c is a constant that is put there to the property that we really need from a uniformly expanding is that eventually the derivative is going exponentially fast. But you might have, by the chain rule, you're always iterating this, so you might have a situation where the derivative along a point, there are some points where the derivative is small, okay? So initially the derivative might not satisfy this bound here, so you need to have a c, but if you keep iterating, then eventually the expansivity dominates. This is not necessarily the case, but this is the condition that we need for uniform expansivity. Okay, this is the definition of uniform expansivity. For example, in the quadratic case, this is not the case, right? In the quadratic map, here you have a point where the derivative is 0, right? And so for that point, you will never, or if you take any pre-image of that point, at some point when you multiply the derivatives, if this point maps onto a point that has derivative 0, then you will have one of these terms is 0, and so it will, the whole derivative will become 0, right? So it cannot satisfy this property here, okay? Because here you have derivatives that are arbitrarily close to 0, including a point where the derivative is 0, okay? In general, if you have a map that is full Blanche, and the derivative might be even quite small, okay, but bounded away from 0, not arbitrarily close to 0, and then you have another full Blanche like this, then you don't know just by looking at it if it is uniformly expanding or not, because it really depends on what happens to these points. If these points here that have small derivative, they map to somewhere that has big derivative, then maybe the product of the two is already bigger than 1 and you're okay. But if these map to another point that have also small derivative, and then you get stuck in a loop where you keep going where the derivative is small, then you might not satisfy this, okay? But if you're lucky and the small derivative, they map eventually to some big derivative, it may satisfy this. So the reason I'm saying this is because there are two extreme cases. One of them is this one, where the derivative is bigger than 1 everywhere, then you're guaranteed that this holds. There's this case where the derivative is equal to 0, in which case you're guaranteed that this does not hold, okay? And then there's many intermediate cases in which it's not obvious by looking at it whether this will hold or not, okay? But in some cases you can prove that it does. Like in the Gauss map, I will leave it as an exercise to prove that it does. I will write it down in a second. So the theorem we're going to prove is the following, is that theorem if f full Blanche C1 actually in this case I will need it C2. C2 on each branch is C2, full branch, C2, uniformly expanding or satisfying these two properties. So we have one is uniformly expanding, and 2 is that it satisfies the following property: supremum over all the partition elements of P of the supremum over all xy in omega of the second derivative of f in x over the derivative of the derivative f in y squared is less than or equal to k. So suppose there exists c lambda and k greater than 0, okay, such that this holds, then f has bounded distortion. No, then something better than that. Then there exists k tilde greater than 0 such that for all n greater than or equal to 1, for all omega n in Pn, and for all xy in omega n, we have that the log of df n x over df n y is less than or equal to k tilde f n x minus f n y. So let's look at this statement a little bit. So first of all, the assumptions, okay? So the assumptions are that f is uniformly expanding. And uniformly expanding, an observation that I should have made before is that one of the key characteristics, what we're trying to achieve here is criteria that will give bounded distortion based on just one iterate of the map. Right? Because the problem with bounded distortion is that it contains supremum over all n. Right? That's what makes it difficult. Okay? Now, uniformly expanding also, in some sense, it looks like you need to know the map for all n. But as we saw, for example, in this case, there are some cases, which are most of the cases you look at, where if you look at, you see the derivative is bigger than 1, you just look at the map, the derivative is bigger than 1. Okay, then it's uniformly expanding. And then the second one, where this is just the original partition, right? This is just the partition of level 1, right? So the partition on which the full branch map is defined, and what it's saying now is you don't need to iterate. There's no n in this, okay? So this is just looking at the map itself, okay? And this is looking at, curiously, it's looking at the second derivative. So now you look at each element, you look at each of the each of these partition elements, and for each partition element you actually look at the second derivative as well as the first derivative. Okay, at the moment there's no reason why intuitively this should make any sense. Okay, it will make sense when we use it in a calculation to prove this, but at the moment you look at a point, you look at all the points, and you take the second derivative of x, and then you divide it by the first derivative squared. Okay, and this could be whatever it is, okay, but you take the supremum over all possibilities here, and you take the supremum over all intervals for the original element, and you show that this is just bounded. Okay, and the consequence, the remarkable consequence, is that these two conditions imply something that is true for all n, right? And this is the distortion, right? Because this is saying for all omega n Pn, for all xy and omega n. And this is the reason why I put this instead of writing the supremum over all omega, is because this gives a very useful bound which is much more specific. Okay, this is a kind of Lipschitz property of this, right? This is saying, in some sense, This is saying that this is less than or equal to some uniform constant times the bound that depends on the distance of fnx and fny. So if you take 2 points that are very close, so that fnx and fny are also very close, then this will give a much stronger bound. Right? It's really telling you how this goes to 0 in some sense as x and y become very close. But in particular, it also gives a uniform bound here, because what is the bound for fnx minus fny? It's just 1, right? Because fnx, fny, they belong to the interval, so this is less than k tilde. Okay? Which means that this term is always less than some uniform bound that is independent of n and omega n in the points. So this is exactly bounded distortion. Okay, that the supremum for all n, for all omega n, for all x and yn is uniformly bounded. Okay, is exactly what we've got. We just have a stronger statement here, which will be useful in our calculations. Okay, this condition here. Okay, in particular, F has bounded distortion. So next week we will prove this, and I think maybe we can just do the verification for the Gauss map. So we basically, so remember we had the proposition that the Gauss map has bounded distortion. Okay, Gauss map. So we need to prove those two properties. Yeah. So I will just sketch okay, so Gauss map f of x equals 1 over x mod 1. So I think the uniform expansivity I will maybe leave as an exercise. I think it's an interesting exercise. Uniform expansion, expansive expansion exercise. I think that the little interesting and non-trivial part of this exercise is to show that is to find the c, the constant c, right? So you can easily, so this is the point where the derivative is 1. Okay, so, and here it's very close to 1, but it's bigger than 1. Okay, what you want for uniform expansion is somehow you would like it to be uniformly bounded away from 1 everywhere. Okay, but it's easy to see that the second derivative, for the second iterative of the map, the derivative is bounded away from 1. Why is that? Because here, where the derivative is close to 1, where is the image of these points here? It's very close to 0. Right? The image here is very close to 0. Okay? And what is the derivative at points very close to 0? It's very large, right? Because here you just have these just getting larger and larger, these derivatives here, right? So here, if you, for example, to prove this, you just take some point here, yes, at which the derivative is something, whatever, or maybe you take some point here, and for all the points from here to here, then the derivative is uniformly bounded away from 1, right? And then the second iterate is also, you look at all the points which map to a neighborhood of 1, they come from points that have very large derivative, so the product of the derivative is bigger than 1, and if you take the points that are here, that are very close to 1, they map here where the derivative is large. Okay, so you need to do a little analysis of the region close to 1 and outside 1 and show that the second derivative is equal to 1, is bigger. If you take the second iterate of the map, the derivative is always bigger than 1. And then you need to show how to translate this to the notation with constant c. Okay, so this is not a completely trivial exercise. I mean, it's not difficult at all, but it's a perfect way to digest a little bit that definition of uniform expansivity. Okay, and then we need to prove this property here. Let's call this property star. This is actually a property that would be quite relevant. So how do we show that it's got star? So, okay, so the derivative, what's the derivative of the f of x? The derivative is minus 1 over x squared, right? And the second derivative at x is 2 over x cubed. Is that right? I think so. Okay. Just taking the derivative of 1 over x. So we need to compare the second derivative with the square of the first derivative. Okay? But we need to compare it not just at x, because if we just compare it at x, it's easy. Right? But we need to compare it at 2 points on each of these intervals here. We need to take the maximum and the minimum over all of these. Right? So what is an interval here looks like, take some interval here, is always of the form basically 1 over n plus 1, 1 over n. This is the form of all these intervals, right? 1 to 1/2, 1/2 to 1/3, 1/3 to 1/4, and so on. Right? So we need to take the worst possible cases. As you said here also, this is monotone. This derivative and the second derivative are both monotone, right? So when we look at d2fx, we just get, so we have that, what do I have here? Second derivative, which is on the top. So the second derivative of f on omega is less than or equal to, so for x, we take xy in some of these intervals, and this would be less than or equal to the second derivative at the left endpoint, right, because this is the worst situation. So this is at the point 1 over n plus 1, okay, because that's where the second derivative is bigger, so we're trying to bind this above, and this is therefore equal to 2 over n plus 1 cubed. Okay, this is basically the derivative at the left endpoint. Sorry, this is 1 over n plus 1, so this is, yes, 2 n plus 1 cubed. And then we have the first derivative. So the derivative here is always less than equal to this, right? So the derivative is less than equal to this, which is equal to that. Okay, for all x in this interval, the second derivative is less than this, and the first derivative, the f of y, is greater than or equal to the derivative of the right interval, the derivative 1 over n, which is equal to 1 over x squared, so we get n squared. Okay, this is greater than or equal to, and therefore the ratio, so this should be coming out, so therefore d2f x over d f y squared is less than or equal to 2 n plus 1 cubed over over n squared squared. Right, so over n to the 4th. That's what saves us, the squared there. Okay, and so in fact we get, in my notes I wrote down an explicit value, so this is actually so I wrote it as so 2, what do I have here? N cubed. Okay, for some reason I get less than or equal to 16, which I'm not exactly sure now how it comes out, but I think that should be okay. Okay, I think it seems that should come up. Anyway, we get an explicit bound for our k. Anyway, it's obvious that there exists some k. Okay, this is going to 0. It's because you just take n equals 1, I think. You just take n equals 1 and you get that's the worst case, yes. Okay, so you see this, so we will finish here, but this is the, we have, rather than proving that the Gauss map itself is bounded distortion, we state a general theorem, because what we're interested in, Gauss map is just our example, okay, but we really want to be dealing with much more general full branch maps, okay. So now we have two criteria, which are these, okay, which are criteria, as you can see, which can be checked in specific examples. They do not depend on infinite iterations of the map. You just need the derivative bigger than 1 for some iteration of the map. And then in this particular case, we can check it with the formula. In other cases, maybe we have other information to check it. So these two criteria, they imply this property, which is the bounded distortion, and that implies that Lebesgue measure is ergodic. Okay, by what we proved before. So we've reduced the situation to a class of maps that satisfy these two conditions, and under these two conditions, full branch maps uniformly expanding and satisfying this condition here, then Lebesgue measures are ergodic. Okay, so next week we will prove this theorem, and then we will go on to. Okay, okay, thank you very much.